This paper, LoRA versus full fine-tuning, an illusion of equivalence. This has come out on August 28, 2024, which means it came out on Monday. It has gained some attention. Already, I noticed that as we are talking about this paper, there's a bit of chatter on the internet, but most of this chatter seems to be AI generated, mechanistic interpretations and readings of the paper, or auto-generated podcasts. So what is this paper about? I'll go very quickly over fine-tuning and LoRA. And when I talk of LoRA, I'll talk about the vanilla form of LoRA. Now, LoRA has gone through a lot of evolutions, a lot of variants, and itself has progressed quite a bit. This paper in particular uses the baseline LoRA, the original LoRA, with all its without any of the advancements that came subsequently as the reference point, and which is fair enough because it's a simplified, the oldest LoRA is a simple LoRA. And using that as a baseline, it makes a mathematical point. We are going to learn about the point that it makes. So let us start a careful reading of this paper. First, just the title. So as I said, LoRA is a fine-tuning technique. It's a specific model fine-tuning technique. When we talk of fine-tuning technique, obviously we imply that we are in the world of transfer learning. We are trying to fine-tune a very large model that it would not be practical to from the ground up, fully train. We wouldn't have the data, we wouldn't have the compute to train the model from scratch. And it wouldn't be very particularly beneficial to train a model from scratch, even if we had those resources. So we live in the world, so just to set the assumptions clear, we are talking of the world of transfer learning, where it's a two-phase solution. The first phase is of someone with plenty of resources of data and resources, trains, compute resources, trains, or the word we use is pre-trains, or foundational model, let's say. When you pre-train, and the implication is these models are large, very large. Now, to train a very large model, the neural scaling law says you need a lot of data, you need a lot of compute, otherwise you won't be able to effectively train a very large parameter model. What would happen is it would start overfitting to the data, memorizing the data rather than having any capacity to generalize from it. So this is the step one. You end up, the output of this is a foundational model. Then comes the second part, which if necessary you do, which is to fine-tune. Fine-tune is a process of adapting it to your particular problem and making it do that thing better. Now, usually what happens is these so-called foundational models, they are trained to solve a slew of related problems. For example, if it is a foundational model for natural language understanding, then it can do, it could be able to do classification, sentiment analysis. If it is an encoder model, it could be able to predict fill in find the word that is missing. And whether given a question and an answer, tell whether the answer pertains to the question or not. Given two sentences, tell whether the second sentence is an entailment to the first or not. And if it is a decoder, if it is an autoregressive model, then it could tell. It would generate things, and you could do all sorts of generations, like language translation, language summarization, abstractive summarization, and so on and so forth. So generally, foundational models are trained on the whole world's data. Because it is trained on the whole world's data, it tends to have a certain general purpose quality to general purpose quality to it. It is not specifically necessarily the best thing that you can apply to your problem or your domain. So your first approach is you try a foundation model, and if it works for you, great. You don't have to do anything. And for a vast majority of people, and the usual practice is to just download a foundation model and use it in inference mode. When you use it in inference mode, the amount of compute resources needed are orders of magnitude smaller than the amount of compute resources needed to train the model, pre-train the model. However, if you want a little bit better performance on your specific problem domain, then you get into the business of fine-tune the model. You take the foundational model, you bring your own data, your fine-tuning data, and usually the size of this data is not as big as the size of the pre-training data. Pre-training data, you pretty much feed these language models just about everything you can get uh, in a digital form. It is the whole web scraped. It is whatever your company has in addition. Google has in addition images, or Facebook has in addition images. You'll fine tune, you pre-train a model with that. It's a massive, massive undertaking. But when you fine tune a model, you might be looking at rows like between 100 to, let's say, 10K, or at most maybe 100K rows. Going to million is usually considered uh, rows of data, or let me just use the word instances of data. Uh, Instances of data. That is what you fine tune with. Now, the very thought that you can fine tune a large model and adapt it and make it do better on your thing, you could argue that it could be for two reasons. One is that your data has a slightly different um, distribution, data structure distribution than the general purpose data. Or it could be because, let's take an example. A general purpose data can tell that this is a tree and not a truck and not a cat. But you want to be very specific. You want to tell a pepper tree from a weeping willow, and not just a pepper tree from a weeping willow. You want to be able to look at the picture of a pepper tree, for example, and maybe deduce whether it's a healthy tree or whether there's a fungi, whether it's infected or diseased, and which particular disease that a pepper tree is suffering from, right? So, in other words, now you're in the domain of a forest office, a forestry and botany. In such a situation, you might find that your general purpose model is not so good, and you need to further refine it by showing it something that probably the foundational model was not trained on because the data was not accessible. And you, as a specialist, have access to that domain specific data. So you can fine tune it and make it better in that area. So that is it. So your data distribution is slightly different. You have more data in a very narrow area, and you want it to really do much better in the narrow area. So that is the scope of fine tuning, and therefore the two legs of transfer learning. Now that's a very broad view of the whole subject. Now, when you do fine tuning, there are three ways that you can do fine tuning of model. You can do a full model fine tuning, which means that suppose you have a model, so methods of fine tuning. Let me just write it down. Broadly, a full model fine tuning. What it means is, suppose you have a model M0, you unfreeze the weights. You open out all the weights, all the parameters of the model you open out, and then you go through, you bring the fine-tuning data, pass it through this, and you do back propagation of the gradients with respect to the theta, right? You do that, and then your weights here change. So you could do that. This is the loss. You would have a y hat, and then therefore there would be a loss between y and y hat, because you have labeled data x, y. The usual process of machine learning. You can do a supervised fine tuning, a full model fine tuning. The B is you could say, you know what, I know that I don't need to do full model fine tuning because I know that different layers of a model, they do different things. So for example, if you're looking at, um, let's say, a transformer model dealing with text, the early layers, they just look at the word positions and they look at the individual meanings of individual words. But as you go deeper and deeper into the transformer, then what happens? The later attention layers, they're dealing with higher order abstractions. So for example, if you want to improve something which is much more a higher order, like for example, abstractive summarization of text, then you're much better off, dealing with the later layers. So you can do, so you know which layers to go after. And so you can do layer selective fine tuning. This, by the way, is interesting because just recently, I think it was just in the last, I would like to say in the last 24 hours or 48 hours, Meta has released yet another paper talking about interesting way actually to replace the next token prediction with something else. But anyway, that's a digression. So this is layer selective fine tuning. And then there is the parameter efficient fine tuning. Parameter efficient fine tuning says that leave the model alone, leave it frozen, right? Leave it frozen. Don't touch it. Instead, go touch some auxiliaries, introduce some auxiliaries, right? And in a very hand-waving way, what you could do is your input goes in, X goes in, Y hat comes out. So you could, for example, append some soft prompting vectors to the input itself, or you could do something to the weight, just do an additional business with the KQV, the KQV kind of a weight. You do some scaling or something like that, some simplification. You can, what you do in a sense is you train, the main idea is train some auxiliary parameters, leaving the main model alone. Right? And performance efficient fine tuning has emerged as a dominant way recently to fine tune models because it democratizes fine tuning. The former two methods require, the first method in particular, requires a lot of hardware resources. Right? You have to load a model, you have to open up the weights. The moment you open up the weights, now you need to have memory, not just to store the weights. You need to be able to store the gradient of the loss with respect to each weight. And you have to be able to save the quadratic form also, the quadratic of it also. So the memory utilization literally becomes I would like to say three and a half times what you would need if you were in pure inference mode, a minimum 3.5 times memory. Now, at a time when you and I, normal Joes, make do with simple 4090s, right? Or maybe if you're lucky, with one A100s, right? We don't have the luxury of full model fine tuning. So in such a world, when this parameter efficient fine tuning techniques came out, they were considered a blessing because all of a sudden you and I could go and train a very small number of auxiliary parameters. They would be less than typically 1% of the size of original or base model, much smaller than that. And amongst the parameter efficient fine-tuning techniques, there's a family of techniques which became LoRA family, which is very, very popular, perhaps the most popular. And if you have any doubt, the kids, I mean, whether we as, the ironical thing is that the younger generation, the kids are much more aware of it than we are because they do a lot of image generation. If you go to Savit AI or any of this image generation websites, you will notice that they're doing amazing, amazing things. And if you'll just forgive me the digression, I will just go to one of them. I believe which somebody pointed out, and it was you literally see LoRA in full effect there. And I'm using this as setting the context for this paper. So first, before we talk about the limitations of LoRa, why don't we look at the power of LoRa and how ubiquitous it has become? So this is a website that contains lots of beautiful images. And let's take an image that perhaps, as you can imagine, these are very creative images, and the kids are all over it. They're doing very, very creative and remarkable things with it. So let's take something where I can discern clearly the use of LoRa. Maybe this one. This one I'm fairly sure has a LoRa attached to it. So it is using this checkpoint. No, I don't see a LoRa directly used here. Let's try another one. How about this one? Oh, yes. So you notice that here is this picture of a bee. And there is a prompt, as always in image generation. There's a very well-crafted prompt. And obviously, as you know, it takes a tremendous amount of expertise to be able to write such good prompts. And then this bee is bathing what seems like a bathtub of honey, as far as I can make out. Okay, so now you notice that there is a base model, but the base model is getting effectively fine-tuned or is being improved upon by a flux, fantastic detail, and double exposure magic. What does that mean? Let's go into look at any one of the LoRa's. What does the double exposure do? We can find out. There is no detail mentioned here, but more details. Thank you. Introduces the double exposure LoRa model, a versatile tool crafted to bring the surreal beauty of double exposure effect to life. This model seamlessly blends diverse elements from cosmic blah, blah, blah. So this is some artistic thing that it adds an artistic touch to images. And so the previous image obviously has used two LoRa adapters over the base model. And it just goes to show how the practical utility world believes LoRa to be almost a given, a de facto, very useful tool. LoRa adapters are composable. You compose them for different effects. You want to add jewels, for example, to the bathtub. I'm sure there is in fact a LoRa adapter that will go and add all sorts of jewels all over the picture wherever it finds a solid surface. Right? So kids have been doing, and the creative artists have been doing amazing things with this fine-tuning LoRa adapters. Right? But this paper asks a very interesting question in a serious way, and we'll go do with this. So what does this LoRa family of fine-tuning models do? It is as I said, it's an auxiliary model that you layer upon, very much like Facebook, Adobe, in a picture you add layers to generate in an additive way. So, so here's an example that I can give. Suppose you take an image, and I imagine that you want a LoRa adapter that gives it a more young person's look, right? I'm sure there's a LoRa adapter that you can do to a picture. You generate a picture, let's say that generate a picture of a person, and but then you want to give it a very particular look. You might have a LoRa adapter for that, right? You might have a LoRa adapter for a particular hairstyle and so forth. And these things truly do exist. And so the advantage is that you can take M0 base model, and you can have LoRa L1 and LoRa L2, and given an input, it gets, so it's a scatter gather approach. You feed it to each of these models, whatever, let me call it Y0, Y1, and Y2 that comes out, you add it all. Add it to get your final Y hat. Y hat is essentially Y1 plus Y2 plus Y3. In some sense, it's in a way, I'm obviously speaking in a very notional way and glossing over a lot of details. That's the basic idea of LoRa. LoRa, the term LoRa stands for low rank adaptation. Low rank adaptation. what it is trying to say, and I think I'll try to give you the gist of the idea of LoRA before we get into this paper, is that, see, suppose you fine tune a model which is very good at, let's say, classifying an object, imagine it, whether it's a car or a baby or a truck or a tree or a house and so forth, a general purpose foundational model. And you want it to become really good at being able to tell um, types of, or distinguish between pepper tree and weeping willow, or being able to tell all the subspecies of, let's say, pepper tree or the weeping willow, or whether there's any particular specific disease that the tree is suffering from, or determine the age and whatnot. You want to do some very unique thing to it. So you can imagine that if this model is there with a set of weights, base model, right? Base model. And you bring in a small amount of data, fine-tuning data, and your goal is to create a new, let us say that you were to do a full model fine-tuning. So your fine-tuned weights are, let us say, WF, right? And this is your original weights. W0 are the original weights. You would agree that when you look at delta W, which is equal to fine-tuning minus W0, just intuitively think, you would not imagine that every single weight has gone through drastic change, isn't it? You would imagine that the weights have gone through, some weights have gone through almost negligible changes. In fact, most weights have gone through almost negligible changes, and some weights have gone through drastic changes. Right? A few of those, a minority would have gone through a lot of changes. So now let me make it very concrete. Suppose you're looking at two layers, and just for the sake of simplicity, assume that these are dense layers. So this is layer L, and this is layer L plus 1. So between these two layers, there is a, output goes to input and so forth. So there is obviously a matrix, right? So let us specifically say that this is the original matrix between these two layers, the weight matrix between these two layers, right? By the way, when I say weight, I'm not ignoring the biases. Subsume it, put it, an augmented weight matrix contains the biases also. So parameter matrix. So then you have the weight matrix. So when this weight matrix goes through, let's say that you fine tune the full model, it becomes this from the original to the final. You would agree that it would be pretty astonishing if a very small amount of data fine tunes this model and all the weights, all the values in W0 go through radical change. That would signify a pretty strong degree of instability, isn't it? The main idea is that these weights have captured and understood how to think about images. It just needs to understand just a little bit more the nuances of telling a pepper tree apart from a weeping willow, or the kinds of pepper trees, or some very, very small additional thing needs to be. So one common analogy that I could give, sort of a hand-waving argument, is that if you want to hire a kid for, let's say that you want to hire somebody for machine learning in your for your particular problem set. Let's say that the problem set that you're doing is unique to you, some very specific biology or medical problem. You have two choices. You can, of course, start with a kid, a kindergartner, and train that kid from the ground up to become really good in your stuff, right? Well, that would be foolish. That would be like pre-training a model and going all the way just on your data or for your purpose. Other way that you could do is you could go get a college, a computer science college graduate, somebody who's trained in AI. So that person is a general purpose AI engineer. And now all you need to do is train that person to be a little bit better at solving your kind of problem. So the logical thing is to go hire an AI engineer and then put that person through some maybe 1 or 2 months of training. But when you put the person through 1 or 2 months of training, that person is not going and relearning something from foundationally different from what is there in the AI textbooks. It is just learning a few extra things on top of it, right? And so the intuition that I carry is that this delta W is also a matrix of weights, isn't it? It is a matrix of weights, but in these weights, some values would have increased quite a bit. Somewhere here or here, values would have increased quite a bit. But most of those values would be close to zero. Like you would imagine that most of the weights, because I'm looking at the change of weights, most of these would be close to zero, isn't it? So in other words, most of the weights would be approximately zero. They would be like below an epsilon threshold. So most of the Wij specific perturbations in individual weights would be perhaps below a threshold. And if you make a rule that if it is below a threshold, set it to zero, then you would end up with a matrix that has a lot of zeros, isn't it? When a matrix has a lot of zeros, what you can do now is, again, without getting into the weeds of linear algebra, I'll give you an intuition. The intuition is that what you do is, you can interchange the rows and columns of a matrix. Imagine that you could do that and do some transformations. Again, very hand-wavy argument. But imagine that you could settle and bubble down all the zeros to the ground, to the bottom right, and bubble up all the non-zeros to the top left. Right? So you would agree that you could transform this into another matrix in which you have essentially a much smaller matrix hiding in there of the real non-zero values, isn't it? Does that make sense, guys? The rest of it is an ocean of zeros. You could bubble up all the non-zero values to one upper left-hand corner. And let's say that the dimension of the this matrix will have very few rows and very few columns. Does that intuition make sense, guys? So the word you say that the number of unique rows or columns in this matrix that are needed to represent that matrix is called the rank. So that's the intuition of a rank. And so you would say that hiding in this delta W, which looks like a full-size matrix, is a much smaller, low-rank matrix, perhaps, isn't it? Something that can be represented. Or another way of saying it is that you can represent the reality. So this is very hand-wavy, right? So I'm just trying to give you a very hand-wavy idea. Or another way to say it is that the rank or the actual dimension of the matrix hiding in there, effective dimension is much lower. If it is much lower, then I should be able to, geometrically what it means is, the real dynamics is in a much lower dimension space. So what I should be able to do is say that delta W is actually equal to this. I could be able to write it as two matrix multiplications, A, B. What it means is the reality actually exists. Let the rank of this matrix be R. So this is R. Why am I not able to now write on it? Something weird has happened. Okay, I apologize. This thing has frozen on me. Oh, my laptop itself has frozen. What's going on? Are you guys able to hear me? Or do I need to reboot the whole thing? I think you are able to. So I wonder why this has frozen. Okay, guys, I might have to stop this OneNote and start it again, or something has happened here. In fact, my entire screen has frozen up. So, Rai, you are the co-host at this moment?
I am, sir.
You are, right? So, I'm going to reboot my machine. I apologize for this inconvenience. I can't do anything now, it turns out.
Pause the recording before you do. Or let me pause it.
No, it's not letting me click on anything. And so I apologize for the interruption, and I'm going to start it again. So, and let's move faster now. So this is the concept of LoRA. So what LoRA says is that if there is truly a lower dimensional matrix hiding in there, low rank information, the effective rank of the matrix, the way the people think is if the effective rank of the matrix is low, then why not do a decomposition? Because if you do a decomposition like this, a matrix decomposition into a lower dimension, what it does geometrically is it projects data into a much lower dimension and then upscales from there. And so this is the dimension input, this is the D out, but in between is the rank matrix. So this matrix has D in, rank times D in plus rank times D out. This is the total number of parameters in the LoRa adapter. So suppose rank is equal to typically, let's say 16. I'll just take a number. And let's say that the input dimension was 1000 and this was 1000. So you're looking at 16 times 1000 plus 1000. That is just 32,000, right? Which is much less than creating 1000 cross 1000 original matrix, which was a million. Right? So you have much lower dimension. So people project it all the way down to 8, 4, 2, even 1. The rank of the matrix historically in LoRa has varied from 1 to 64. So as you can see, by doing this, a whole new front was opened up in our field of LoRa adapters. Very, very popular. It became the most popular parameter efficient fine-tuning technique. There are many variants of it. There's LoRa, LoHa, Ada LoRa, Dora, and I can go on and on. And last week itself, if you remember, we covered EVA, something that tried to put the best of all the ideas together, right? But we won't go there. Now let's go back and read this paper and see what it is trying to say. Now, what is the advantage of LoRa? The many advantages are, first, you don't touch the original model. You're touching only a smaller model. So computationally, it's very efficient. The second, and perhaps the biggest advantage is you don't risk catastrophic forgetting. The risk for catastrophic forgetting is significantly lower. It is not as much as you would have thought. Very, very rare with the LoRa that you would have, because the original model still remembers the general broad knowledge. So with that background there, let's read this paper. It's a very quick paper, actually. The main idea, it goes into 10 pages to say it, but I think we can get to the idea in 5 minutes. Fine-tuning is a crucial paradigm for adapting pre-trained large language models to downstream tasks. Recent methods like LoRa have been shown to match the performance of fully fine-tuned models on various tasks with an extreme reduction in the number of trainable parameters. Even in settings where both methods learn similarly accurate models, are their learned solutions really equivalent? So the question that this paper asks, and actually I found it rather odd that it even needed to be asked. Even in settings where both methods learn similarly accurate models, are their learned solutions really equivalent? That reminds me of a law that somebody told me in journalism. It says that if the title or the main thesis of an article, journalistic article, is a question, the answer invariably is no. Right? So if somebody says that does, I don't know, will some economic plan lead to recession? It means that the journalist is posing it as a question because he has half-baked arguments, but the broad answer is no. Right? Because if it could be proven, he wouldn't have stated it as a problem. I remember that journalistic thing, and that was my first reaction reading it. First thing is that mathematically, why would you expect that the learned solutions will be really equivalent? A full model training and a LoRa adapter, they would essentially learn the same thing. One of the deep lessons in machine learning has always been that you are in the pursuit of an effective model. There is no correct model. And there's usually a rich variety of possible solutions. In fact, infinity of possible solutions, each of which will work in practice. In other words, those models, each of those models, they may take different routes to answering your question, but they will be able to answer the question so long as the empirical evidence is they are able to perform well on your task. So I don't know what the whole pursuit in this paper is, that you need to have, are the solutions really equivalent? And as you will see in this paper, it takes a very dim view of the LoRA, because it feels that the LoRA approach, rather dim view somewhere along the line, because the LoRA, especially low rank, easy, the computationally cheap ones, they apparently don't learn the same way as a full fine-tuned model. And it is because of a concept that he calls intruder dimensions. So, well, anyway, let's play along with this paper. As you can imagine, I am quite skeptical of the main thesis, because to me, it looks self-evident. We study how different fine-tuning methods change pre-trained models by, and again, I apologize, it is quite possible I've entirely missed the point of this paper. We study how different fine-tuning methods change pre-trained models by analyzing the model's weight matrices through the lens of their spectral properties. We find that full fine-tuning and LoRA yield weight matrices whose singular value decompositions exhibit a very different structure. Moreover, the fine-tuned models themselves show distinct generalization behaviors when tested outside the adaptation task distribution. So let's unpack this. A lot has been said this. So this is the main thing they say. Now let's see. What is a singular value decomposition of a matrix W? See, one way of thinking, very hand-wavy way of thinking about SVD is to think, if I gave you a number, something like 42, right? Supposedly the meaning of life, you know that it is 2 times 3 times 7. Right? So when you break it up into its prime factors, you in some sense understand 42 a little bit better, the properties of 42. So now what happens is, the way, one intuitive way of thinking about any matrix is, a matrix is an operator that projects a point in one space to a point in another space. The other space could be the same space, right? So imagine two spaces, input space. Now, once again, this is misbehaving. Okay, input space, and think Euclidean space that may be in the D dimension, D1, a D dimension space, or N, let's say N dimension space. And then imagine another space, output space of the matrix operator, which is M dimensional space. Then, if you take a N cross M matrix, what this matrix will do is that it will take every point in the input space, every point will get projected to some point in the output space, right? So matrices are essentially operators. In other words, matrices are operators, operator functions. They operate on points in the input space, vectors in the input space, because a point is a vector, let's say input, and then it will project it into a y. Y would be mx, some matrix x. That's all there is to matrix. Matrices are machineries or methods or operators that take points in one-dimensional space and through a linear transformation, and these transformations are linear, some sort of a transformation, they project it down to a point in another dimension. So when they do it, you might want to ask, what is the structure of this matrix? To give you a sense of the structure, suppose they are of the same dimension. So simplified. Let's simplify it. Suppose n is equal to m. So now what happens is you're going from a space which is n dimensional to another space which is n dimensional. So essentially the same space. So a point that was here might end up a point here, which you could represent just as a point here. This is the journey. If you take any, or maybe I'll deliberately pick another point here. So then what has happened is you can say that in some sense, this point has been partly rotated. There is a theta rotation and there is a stretching and a lambda scaling, right? So if you remain in the same dimension space, you could potentially say that what matrices do is within the same space, they partly rotate and partly stretch every point, right? And then comes a very beautiful intuition that if you take all the points in a unit sphere, suppose you take all the points which are in a sphere, let's say, and apply a square matrix, like this kind of a operator, matrix M, to it, it will necessarily make it into an ellipse. Right? That's what it will do. It will make it into an ellipse. And an ellipse has a principal direction and an orthogonal direction, E1, E2. And as you notice, something very interesting that happens is a point that is in the direction of an ellipse, if I just look back at the original circle, this point has gotten only scaled, and this point has gotten only scaled. So there will be 4 points on the circle or on the disk, or the points that are on this so-called principal axis of the major minor axis of the ellipse in 2D. Those points from the circle or from the disk will only get stretched or squished, like basically scaled. They won't get rotated. These directions, and especially, are called eigenvectors, E1, E2, namely what for an ellipse you call the major axis, minor axis in 2 dimensions. These are called eigenvectors. And the degree of scaling that they do are called eigenvalues. This is basic linear algebra that you might remember from the old fog of college days, right? So, and it so happens that there's a bit of math. You can write it as U transpose, U being just E1, E2, and D being lambda 1, lambda 2, literally the 2 eigenvectors. This is what this matrix is. So in other words, if I were to know the eigenvalues and eigenvectors of a square matrix, I would in some sense know its property. What does it do, right? And one intuition that I carry in mind is whenever I think of a matrix, I ask myself, what will it do to a unit sphere? A disk in higher dimensions is a sphere, right? A hypersphere. What will it do to a unit hypersphere? Right? And it will do something like this. And now generalize to non-square, like you're going from m dimension space to n dimension space. What are eigenvalues and eigenvectors in this current situation becomes, with a bit of generalization, singular value decomposition. That's a basic intuition. So you should always ask that any matrix, therefore, a non-rectangular matrix M can be written as U, D, a diagonal matrix, V transpose, right? You notice that the only difference between a square matrix and a non-square matrix is V and U are different. They are not the same, right? That becomes a SVD, singular value decomposition, right? Because you're projecting to a different dimension space. The point of singular value decomposition and the reason eigenvalue and singular value decomposition are considered crown jewels of linear algebra is that they sort of elucidate the property of the matrix. Right? They tell you what is it going to do. And the way I think about it is, what is it going to do to a unit sphere? Right? It gives you intuition about that. And generally what it does quite often is that if you have data, it tells you which directions matter more than others. Like, for example, this direction, you can say is most important. You have the most variance of the data along that direction, along the first major axis, and less along the second major axis. And it helps you do simplification of the problem. In fact, principal component analysis is literally based on the fact that you can just keep the first few vector dimensions and throw away the rest. And that's what it means to, when I made this very hand-wavy argument that deltas could be essentially represented with just a few perturbations, meaningful perturbations. The rest are zeros. What I was trying to say is, in a more fancy way, the singular value decomposition. So that's what they're talking about. So what they say is that, see, if you, the main gist of the paper, and I'll get to it, what they say is that if you take a full model, M naught, and you go from here to M fine-tuned, right? So what will happen is you can have your eigenvectors or singular value vectors, the general singular vectors of the original model of M0, and you can take the singular vectors of the fine-tuned. And when you look at these vectors, what you see is that those singular vectors, especially the important singular vectors, let's say that you look at the first 50 singular vectors. When you do a full model fine-tuning, then what happens is the singular vectors are more or less preserved. The important singular vectors are preserved, right? So what it means is the machine does not come up with a completely different reinterpretation of reality, which is a good property, right? And which is desirable. But what this paper is saying is that, on the other hand, if you do LoRA, especially LoRA with very drastically reduced rank, what you notice is that LoRA, because in LoRA, you have some singular, see, think about it this way. You have singular vectors of the M naught, the original model. But then you have done this thing, which is completely independent. And if you think about it, what the LoRA captures is the differentiation in the data. Like, how does this fine-tuning data differ from the original data, right? That is what it is. That's what it really captures. So what it does is, when you train this machine, you realize that it comes up with its own sort of a eigen vectors. If you consider these two models as one joint model, you expect most of these initial singular vectors or directions of importance to be preserved. But what they notice is that LoRA introduces what they call intruder dimensions. Like, there are other directions into the dimensions. Another way of putting it is that there are extra eigenvectors that show up that were not there, right, in the original model. So it is almost like the original model is saying, you are in a plane, reality is in a plane, right, the principal reality. But this guy is saying, no, it's I'm adding one more z-axis to it, and there is an extra dimension in which the fine-tuning data is now getting resided. Now, to me, that looks to be a good idea to do so, but for some reason, these authors believe, no, that's not a good idea. Okay? And that is the gist of what this paper is saying. So now that I've given you the big picture, let's go through the paper and read through it. So what they are saying is, and I'll just go through the pictures to explain what the paper says. If you compare the eigenvectors, each fine-tuned models, singular vectors of the fine-tune, and you compare it and you see, let us look at the similarity to a vector of the original model. You will notice that, as this diagonal line shows, there is a very high degree of similarity between the original vector and the fine-tuned eigenvector. Even the order sort of is preserved, right? There's a very, very high degree of similarity. But observe that if you take a LoRA fine-tuned model, even with 64 dimensions, what you notice is that, so let's observe this picture in a blown up way. Let me blow it up a little bit. So do you notice that so let's see what all things happen. First, sorry, this is huge. First, observe that there has been a shift in this direction, isn't it? So every vector seems to be correlated with another vector But so you would expect the third vector to be correlated, the third fine-tuned sort of singular value vector to be correlated or pretty much be the same as the third original singular value vector, singular vector. But instead, what happens is the third fine-tuned vector in LoRA will find that its original guy was the sixth one or fifth one. So if it is the fifth one, what has happened in between? Two additional vectors have gotten injected, isn't it? That are more prominent than the third, being considered more important than the third. So that's the mathematical argument, and that is why you see the shift, right? Because you notice that it's a shift towards the top left. It means that some additional vectors have intruded in the list of vectors. So let's say that the initial singular vectors were V1, let me just use the word S1. Singular vectors originally was S1, S2, S3 in the original, right? And now what has happened is after LoRA, you are getting S1, S2, intruder, some intruder A, intruder B, and then S3. Right? I'm just sort of giving you a basic intuition. And then somewhere again, you'll find some intruders. These are called intruders. Singular value vectors are popped in there. And what they're saying is, and I'll sort of distill it now, the paper, what they're saying is, the smaller the rank, the more the compression, the more you see these intruders come in. Now, you would say, why are you so alarmed about it? Why are you so upset about this? What's the big deal? And that's what I'm puzzling over in this paper. I would have expected something like this because this low rank adapter would discover its own subspace, embedding subspace, in which to project the data. And some of those vectors would obviously be orthogonal to all the previous eigenvectors, singular value vectors. So the big question I was puzzling over is, so what's the big deal and why are you so upset about it? So let's go and think what they are trying to say, and maybe I'll get the point. Maybe I haven't gotten the point of the paper.
I mean, the only equivalent I can think of is when you're sampling a signal and you're sampling below the Nyquist criteria.
No, they don't get it.
I got it. Getting aliasing over there, and that's what the bias.
Yeah. So from an information theoretic perspective, if you go below that criteria, then obviously you're doing it wrong, right? But they don't use that argument. They don't use that argument. You'll see. So see, here's the thing. The proof of the pudding is in the eating. If I have a specific task, let's say all I'm doing is putting, let's say if I'm talking images and I am just adding a little glow to the picture. Now, see, I have a trade-off. When I create a LoRA whose job is to create a glow, I'm gaining an ability, namely to add a glow to the picture. Then it is obviously true that the fine-tuned model, which is composed of the base plus this, will not be able to do other things as well, isn't it? Because I've biased it towards specialized it towards this. Okay. So there is always a give and take, right? One would imagine there's a give and take for everything that specialization that it's like, you have a car, general purpose car, but every time you put a massive engine into it and specialize it to do racing, you put fat tires. Now you can't complain that the ride has become very bumpy, right? Because sports cars are not supposed to give you a boat-like smooth ride. That's the question that I've been asking, that every time you specialize for one task, you consciously know that you are creating a LoRa adapter for one particular task. And it is so easy not to use that adapter. It's composable. At runtime, you decide, inference time, you decide which adapter to use and which not to use. So what is the big deal? So anyway, these people go and they point out that, look here, look, we discovered there are these intruder singular vectors are popping up, and that is causing the shift, right? So very good. It does cause the shift. By the way, there's a bit of theory that I should talk about. There is this whole question of rank stabilization. Like what happens is when you try to what rank is appropriate, you have to be careful. Otherwise, what you can have is you can have gradient explosions. Like if you make the ranks too low, right, then too much signal is doing the fine tuning, trying to back propagate and so forth. You'll have strong gradients. You can have rank collapse, literally. So all sorts of problems are known, the stability problems, but those people have known how to handle it. So a lot of the way that you do it is by bringing in these hyperparameters, little way that you do it. And by the way, this one, it says that they used 2R, but the original paper used 8R and so on and so forth. The original LoRa's used 8R, but we won't go there. He goes into the theory of singular value. These people go into the theory of singular value decomposition and the vector similarity, cosine similarity, and so forth. And what they say is that when you look at intruder dimension, that you introduce vectors whose similarity is not enough, based on how you define the similarity, the number of intruders begin to rise, right? Very obvious sort of things. But the main points that they make, the findings that they do is full tune updates have a higher effective rank than LoRa adapters, even when the LoRa is performed with a full rank matrix. So it says that if you use an auxiliary matrix and tune that instead of tuning the original matrix, then the original matrix will have a higher effective rank. Effective rank is the concept that what is the real embedding of the data, in what dimensional space is it truly embedded. Most of the information is truly there. So the full fine tuning has a higher embedding than the LoRa ever has. And I don't know why that is alarming, but I suppose it's a finding. Intruder dimensions are distributed across both high and low singular vectors. So it says that, see, if you see, they get interspersed everywhere amongst the important singular values, amongst the not important singular values. Again, I don't know why this would be, why would I be alarmed? But it is, it's so. Intruder dimensions increase in magnitude and change in direction as fine tuning proceeds, which makes sense. What they are saying is, this may be of significance actually. What they are saying is, as you train the model, these intruder dimensions, these dimensions that the LoRa is finding, it changes direction. It says first this direction is important, then it begins to say, no, it is this direction that's important. And how important it is, the scaling, the singular values begin to change. Once again, isn't that the whole point of training? The training is the search for those singular vectors, and it will adapt and reach somewhere. But for some reason, these people are a bit concerned, and see, they most likely have a deep reason. I can't get it. So maybe I was the wrong person to explain this paper. So scaling alpha, which is the hyperparameter learning, think of it in some sense like a modulates how fast you learn. Not really a learning rate, but how much you listen to the LoRa. It's a multiplying factor for the LoRa. How dampened down you keep the LoRa or take it seriously. Those things matter. So there's a lot of details, but they mention this behavioral difference between LoRa and full fine tuning. At lower rank, LoRa adapts less robustly during continuous learning by forgetting more of the previous task. Basically, LoRa is an adapter on the side. It frankly doesn't know your previous tasks at all, right? So at very low rank, it will come up, it is seeing only the new data. It's back propagating on only the new data. If it is back propagating on only the new data, then LoRa plus the original model is likely to have some contradictions, like, it will degrade the learning of the original model. And so there will be some net effective sort of forgetting that will show up, in my view. But I suppose, once again, I'm still puzzling over it. For LoRa models fine-tuned to equivalent test accuracy, we see a U-shaped curve that identifies the optimal rank of fitting to the downstream. So this we notice that when you use LoRa, and this is an interesting observation, I don't know if it was well known, that there is an optimal low rank at which things work really well, right? Which I would call the intrinsic dimension appropriate for the LoRa. So now they go on to say, why do intruder dimensions exist at all? Their hypothesis is this: adding a random vector to a pre-training matrices introduces. See, this is a fact. If you have some singular vectors in a very high dimension space, or you find the data you believe is embedded on a hyperplane, in very high dimensional spaces, any random vector you take is likely to be orthogonal to this, right? So here is an intuition that I'll give you. So if you look at like geometrically, if I have a line, but the space is two-dimensional, any random vector I do is likely to be obviously not aligned to the line, isn't it? Not aligned to be the x-axis. It will be along some other direction. Now, in two dimension, you say, okay, but it's not orthogonal. Now you go to three dimension. You have a page, x and y axis, and any vector that you think is now likely to be obviously off the page, right, in some direction. Now, it's a fact that when you go to higher dimensions, there is so many possibilities that it's very easy to find a direction that is orthogonal to any subspace that you pick, right? They will not be 100% orthogonal, but mostly orthogonal, right, to that. And so when comparing, etc., it's a scalar greater than the largest singular, etc. So that's the point, that when you do it, you'll find some orthogonality. And they're saying that those are the things that introduce this, that if you just train a LoRA separately rather than fine-tune a full model, it is much more likely to learn along those orthogonal directions and therefore introduce intruder dimensions into the solution. That's the main point, I suppose, which I completely agree with. That's the explanation of why it should happen. It is happening. So I think their hypothesis on why it's happening is completely correct. And I completely agree with it. What I'm not understanding is, so why are we so alarmed and upset about it? But I would like to hear from you guys if you have an idea, or if you could explain to me, what am I missing here? All right, guys. So this was the paper reading, basically, the gist of the paper reading. Any questions, guys? Oh, by the way, I don't know, this was a bit technical, a bit mathsy, and I tried to simplify the math. If you remember your singular value decomposition and a little bit of differential geometry, thinking in terms of then it's a lot easier to get a hang on this paper. But otherwise, it can get a little techy and a bit mathsy. I mean, it certainly is either saying something very deep because I didn't get the point, or I don't know. Any comments, guys? Anyone? If not, maybe I'll stop the recording so you feel more comfortable. How do I stop the recording? Good heavens. Stop it.